Hello everyone, I am Surendra Jain, Master Teacher of Mathematics in Vedantu. I am teaching mathematics for last 14 years. I have been teaching for IOQM, RMO, INMO, JEE Mains Advanced, okay, all exams related to maths. Okay, I did my BTech from IIT Delhi. Before I start my session, let me quickly tell you about these sessions. In these sessions, I'll be taking few subtopics where I'll be giving you some details which may not be that available to everyone. Once you know these details, you will be able to solve those questions quickly. You will save your time. You will feel more comfortable while solving those questions. In this session, I will be talking about Cayley-Hamilton theorem, eigenvalue, eigenvector. One more thing before I start. Daksh, you must be knowing, who got All India rank 15 this year. He was student of RM 2225. That's a 3-year program of Vedantu. I was teaching him for the entire 3 year and he got 120 marks in maths out of 120 in JEE Advanced 2025. I think Shimon sir must have talked about him in his sessions. Okay, now through these sessions, the objective is to get more students like Daksh so that we can repeat that performance. Okay, so let's start with this session. So here I will be talking about characteristic equation and Cayley-Hamilton theorem. So characteristic equation, what is this? Suppose there is a matrix A of square order n into n. Okay, for every square order matrix, we define characteristic equation by A minus lambda I equal to 0. When you open this determinant, you get certain polynomial. That equation is called characteristic equation. I will explain this through 2 into 2 and 3 into 3 order matrix. Suppose A is ABCD. Okay, then this determinant of A minus lambda I means it would be A minus lambda B C D minus lambda is equal to 0. Okay, if you open this determinant and simplify it, you will be getting lambda square minus A plus D plus AD minus BC, and this lambda also multiplied here equal to 0. So this quadratic equation in lambda is actually the characteristic equation of this matrix A of order 2 into 2. Okay, for 3 into 3, it will be cubic. For 4 into 4, it will be biquadratic. In our syllabus, we normally have questions of 2 into 2 and 3 into 3. So we should remember this result. Now, please see this A plus D, as you can see, it is sum of diagonal elements. We call this as a trace of A. AD minus BC, I think we all know, it is value of determinant of this matrix A. So we can write like this. So for any 2 into 2 order matrix, you should know in advance before doing any calculation like this that its characteristic equation is lambda square minus trace of A into lambda plus determinant of A equal to 0. So that is the characteristic equation of 2 into 2 order matrix. Okay, now before coming to 3 into 3 order matrix, I will like to talk about the Cayley-Hamilton theorem. What is Cayley-Hamilton theorem? It says every square matrix A satisfies its characteristic equation. Cayley-Hamilton theorem says every square matrix A satisfies its characteristic equation. So for example, if A is 2 into 2 order, then we know characteristic equation was lambda square minus trace of A into lambda plus determinant of A equal to 0. So A should satisfy it, means if you put lambda equal to A, it will become A square minus trace of A into, now here also in place of lambda we will put A. Now listen carefully, when it was a normal quadratic, we were just adding the numbers, real numbers or scalar numbers you can say, but when we are making this kind of equation, this A square will be 2 into 2 order matrix. So there will be 4 element, 1 1 1 2 2 1 2 2 here also. So you cannot just add determinant A like this, we will be multiplying it by I. I stands for identity matrix. For 2 into 2, it will be 1 0 0 1. And when you add it, when you add all the 4 elements, corresponding 4 elements, add or subtract, you will be getting all elements becoming 0 0 0 0 on left hand side. Hence on the right hand side it will become equal to null matrix. So Cayley-Hamilton theorem says for any square matrix, if it's the characteristic equation, this will satisfy, this A will satisfy this equation, which means that will be the relation for every 2 into 2 matrix. Okay, now such relation will be for 3 into 3 also and 4 into 4 also, but we will stick to only 2 into 2 and 3 into 3. That is in our syllabus. Before I go to 3 into 3, let me tell you one more thing. Suppose you are given a quadratic like a square minus some scalar quantity p into a plus q into I equal to 0. Okay, this is the relation that is given to you. Can we say that p will be trace and q will be determinant? So I am actually talking about the converse of this thing. That suppose there is a quadratic, we can say, can we say that p will be trace, q will be determinant? So let me tell you, if in that A, if you remember, elements were A, B, C, D. Okay, if this B is not equal to 0 or C is not equal to 0, okay, and or actually A is not equal to D. Okay, any of these 3 things if happens, then definitely converse is also true. Converse is also true. Converse is also true. That means this P will be equal to trace and Q will be equal to determinant of A. Okay, but if all these things are happening, okay, in that case you may get some other quadratic equation also which may not be its characteristic equation. So what I am saying, if yeah, place is there, if B is equal to 0, C is equal to 0 and A is equal to D, in that case A is equal to D, in that case you can see your matrix A will be actually equal to scalar multiple of I 1 0 0 1, because if B and C are 0 0 and A is equal to D, then A will be equal to scalar multiple of I. Okay, in that case we may get some other quadratic relations also which are not coming from characteristic equation, but that's the condition I have told you. One more thing, I will be sharing with you the session notes. Please go through it. Whatever I am writing here you will find there. In addition to that, you will find proofs of all the things, like proof of Cayley-Hamilton theorem, certain properties, whatever I will be talking in this session, those proofs you will find there in the session notes. In fact, the entire thing that I am covering you will also find there in the session notes. Okay, so what I was saying, this is what every matrix should satisfy. Conversely, if this is the condition, then this quadratic means P will be trace and Q will be equal to the determinant. But if this B and C both are 0 0 and A is equal to D, in that case you may get some quadratic which may not be same as the characteristic equation. So be careful in such matrix. Okay, otherwise you can definitely directly write P as trace, Q as determinant. Okay, now coming to 3 into 3. When A is 3 into 3 matrix, which means it will be A, B, C, D, E, F, G, H, I. Okay, in this case the determinant of A minus lambda I means it should be A minus lambda, E minus lambda, I minus lambda, and all other values like B, C, D, E, F, G, H. And if you make it 0 and open it, you will be getting, I am writing it directly, you can verify it, it has to be lambda cube, because there are 3 into 3 rows, 3 columns. So after opening you will get a cubic equation. So lambda cube minus, it will be trace of A into lambda square. It looks like it's similar to 2 into 2. Okay, and then it will be trace of adjoint of A into lambda plus, sorry, minus determinant of A equal to 0. Okay, so here this is the characteristic equation of any 3 into 3 order matrix. Lambda cube, then minus sign, trace of A. It was same in 2 into 2 also, then plus sign, trace of adjoint of A. Okay, then minus sign and then determinant. I think there was also determinant, but here there was a plus sign, but because it was a quadratic. So you can see for cubic it will be like this. Okay, beyond that it will be more complicated. There will be certain more terms, but I am very much sure that first two terms will be same, lambda power 4 minus trace of A into lambda cube if you go for 4 into 4, and the last term will also be same, determinant of A, but in case of 4 into 4 it will come with plus sign. Okay, so this is the characteristic equation of 3 into 3 matrix. Now as I told you, Cayley-Hamilton theorem says it satisfies its characteristic equation. So the relation in matrix would be A cube minus trace of A into A square plus trace of adjoint of A into A minus determinant of A into I, and that will be equal to null matrix. See, this is a zero scalar quantity, that's a null matrix. There will be 9 zeros in this null matrix because we are talking about 3 into 3 matrix. Okay, so for 2 into 2 it's clear, for 3 into 3 you have to remember this is the relation. Okay, now for converse, if you want to know whether converse will be true or not, as I told you, in 2 into 2 the converse was not always true, but certain condition was there. In case of 3 into 3 those condition will still become more complex, so I will not talk about that. So I will not be in position to say that if cubic is given that will be guaranteed to be its characteristic equation, but yes, if you know some A, it will satisfy its characteristic equation for sure. Okay. For this trace of adjoint of A, I will like to tell you one more thing. You will find at certain places instead of trace of adjoint of A. And by the way, you know what is adjoint of A? Adjoint of A is found by taking cofactors of every element and then taking the transpose. But in this case, we just need the sum of cofactors of diagonal elements. Sum of cofactors of diagonal elements, trace. Okay, this is also equal to actually trace of A whole square minus trace of A square by 2. Okay, this expression also gives the same thing as we are getting from trace of adjoint of A. Okay, so this is also something that you should remember. Okay, all these things are given in the notes, so please go through it. Now let's start few questions. So this is my first question, previous year JEE Advanced 2022. We are given this question, m equal to 5 by 2, 3 by 2, minus 3 by 2, minus 1 by 2. Then they are asking m raised to the power 2022. Okay, see, this kind of questions, many people feel that we will get m square then mq and we will get certain pattern and we will get the answer. That is true to some extent, but first you may not be able to get that pattern always, and also whenever this kind of questions are created there has to be some logic behind, and most of the case, in fact in all the questions which I have seen in JEE Advanced, they are inspired by characteristic equation only. Now please see, for this m, I'll write it here. Yeah, so for this m you can see the trace is equal to, trace of m is equal to 2 and the determinant value of m is equal to 1. You can check, sum will be trace of sum of diagonal element is 2 and the value of determinant is 1. So its characteristic equation, and then putting m into it, you will be getting m square minus 2m plus I equal to 0, which means it becomes m minus I whole square is equal to 0, which means if I subtract this m by I, take whole square, you will get null matrix. Now this will make very easy to find this m power 2002. How? Please see. Suppose I write m is equal to I plus n. Okay, where n is actually m minus I, where m is nothing but m minus I. So n square, and if you take higher powers n cube and so on, they all will become equal to null matrix. Now in such relation, because I in matrix is commutative. When you take the product, you can apply binomial theorem. Okay, so this m raised to the power n, if I have to find, you can apply binomial theorem, I plus n whole power n. So in this binomial theorem, we will be getting I power n plus n c1 I power n minus 1 into n power 1. This will be n minus 1, and all other terms would be null matrix, because n square, n cube, they all will be null matrix. Okay, so you can see this becomes I plus n into I power n minus 1 will be I only, and then multiplied with n will give you n. So this becomes I plus n into, and this n is nothing but m minus I. So we got my m power n in general. So this is n into m plus n, actually this would be 1 minus n into I. Yeah, this was I actually. Okay, so this is what my m power n is. Now you want to know m power 2002, you can do it. Okay, I will leave this question here, because after that you just have to plug in the value of n and you get the answer. Okay, in fact there have been many questions. In fact there is one question in our Eklavya module also of similar type, and you can see here also the trace is true, trace is 2, and the determinant is 1. So this will also have the same characteristic equation, same equation, and same method to find a power 100. Okay, this is not a previous year question. My next question is previous year. Now please see, this is 2019 question. Here we are given m as this 2 into 2 order matrix, and we are given alpha I plus beta m power minus 1. Here if you multiply both sides by m, so you will be getting m square minus alpha into m minus beta into I is equal to null matrix. So as I told you, here I can see these two elements, they are not equal in general. In fact these two cannot be 0. So from that converse, I can definitely say that alpha has to be equal to trace. Alpha has to be equal to trace. That means it will be sine power 4 plus cos power 4. Similarly beta, which is actually minus of determinant of m, minus of determinant of m. So if you open it, you get minus sine power 4 cos power 4, and you multiply these two, and then minus minus plus 1 plus cos square 1 plus sine square, and this will become equal to sine power 4 cos power 4 plus sine square cos square plus 2. Okay, now they are asking the minimum value of alpha in the set 0 to 2 pi and minimum value of beta in the set 0 to 2 pi. I think this is simple question. After that you may use certain identities, like this can be written as 1 minus sine square 2 theta upon 2, I think, yeah, 2. Okay, so for this I think minimum value will be half, and similarly for sine square t square, if you take sine square t square as sine square cos square actually as t, okay, so that will become equal to t square plus t plus 2. So by finding the minimum value of a quadratic, you can find the minimum value of this beta. Actually t is sine square cos square, which I can write as sine square 2 theta upon 4. So this t will be in 0 to 1 by 4. Now you can check that for this quadratic, when do you get the minimum value? Okay, see, I will go forward now, because this question after this is just a question of quadratic. I have given the complete solution of this question in my notes, so you can go through there also. Okay, now one more question, and this is again from previous year 2016. Okay, this time they have given 3 into 3 order matrix, and they are asking p power 50 minus q. And what is q? Q is a matrix such that p power 50 minus q is equal to I. Then they are asking for q, q31 plus q32 upon q21 values. Okay, now if you see here, the trace of p is equal to 3. Okay, now if you find trace of adjoint of p, you can check for every element the cofactor is coming out to be 1 1 1 for diagonal elements I'm talking about. So that will also be 3. The value of determinant of p is 1, as it is a lower triangular matrix, only diagonal elements will multiply. So the equation will be p cube minus 3p square plus 3p minus I is equal to 0. So that will be the characteristic equation. Then Cayley-Hamilton theorem use to get this expression. Now you can see this is p minus I whole cube equal to 0. So this is again a simple question like previous one. Here I will take p minus I as, let's say, r. So I can write p is equal to I plus r. Okay, here I am taking r is equal to p minus I. So for this r, you can see r cube term is null matrix. So r power 4, r power 5 and all other bigger term will be null matrix only. So here to find p power 50, I can write it as I power 50, which is I, plus 50 into r. Okay, then 50c2 r square, and then I don't have to bother about the remaining terms because they will all be null matrix only. Now p power 50 minus I is actually q. What is q here? P power 50 minus I. So this remaining thing, that means I can write 50 into r plus 50c2 would be, I think, 25 into 49 into r square. Okay, I will not do this question further because now I think it's very simple question. R is actually p minus I. Here actually you have to find r square also because r square is not null. R cube onwards it is null. R is actually 0, 0, 0 and then 4, 0, 0, then 16, 4 and 0. So that will be r, and r square you can find. I think in r square we are getting all elements to be 0, 0, 0. Only this element comes out to be 16. Okay, so you just have to plug in these values of r and r square here, and please focus only on these elements. 3, 1 element that comes here, 3, 2 element that comes here, and 2, 1 element that comes here. Only these 3 elements you have to take care of, and then you will get your answer. Okay, see this question when this came in 2016, I remember students were again finding pattern. They saw that p minus I, if we do and they take the square and cube, it becomes, after cube it becomes null matrix. But why minus I? That's the reason why it is actually giving you p power 50 in this method. Okay, so please remember these questions most of the time have this Cayley-Hamilton theorem characteristic equation in their background. One more question, 2022 recent question. Beta is a real number and we are given A, and they are saying this is singular matrix. Then we have to find the value of 9 beta. Now first of all, if this is singular, okay, I can first of all I will like to know what is the value of determinant of A, because if determinant of A is 0, then I think it will be 0 for all beta. Are you getting it? Because you can take a power 5 common, and if you take the determinant of it, a power 5 will be common, so its determinant has to be 0. But then there's no meaning of this question. In fact, if you open this determinant in first row, beta multiplied with 0, and then second element is 0 plus 1 multiplied with 2 minus 3, so minus 1. So value of this is minus 1. So this A is not equal to 0. In fact, if I find the trace of A, because I will require this to form characteristic equation, that is beta minus 1. And if we find the trace of adjoint of A, it will be 0 for first element, you can say minus 2 plus 2, so 0. For middle element, 2 element, the cofactor would be minus 2 beta minus 3, plus for this element it will be beta. So this becomes, I think, minus beta minus 3. Okay, now the characteristic equation of this, and then putting A into it, you get A cube minus beta minus 1 A square, and then minus of beta plus 3. Okay, minus sign because it is there in the formula. Here it should have been plus, but because it is minus of beta plus 3, so that's why this minus sign is here, into A minus determinant of A, that is minus 1, so it will be plus 1 into I equal to 0. Now you can see this relation has some connection with this. Now, as they are saying it's a singular matrix, if I write this after taking a cube common, it will be a power 4, 1 minute, not a cube actually, a power 4 if I take common. So that will be a cube minus beta minus 1 a square minus beta into a का determinant, and from the property of determinant we can write determinants like this also, and that is equal to 0. And because this determinant is not 0, as we have seen this is minus 1, so determinant of a power 4 will be plus 1, so this has to be 0. Now I can use this relation a cube minus beta minus 1 a square minus this thing to place it here, and I think we get if I put it here it will be 3a, it will be 3a minus I equal to 0. This will be 3a minus I if I use this relation. Now after that I think this question becomes very simple, isn't it? Because 3a minus I means it will be 3 beta minus 1 here, and then 0 here, and 3 here, 6 here, 3 beta, so 3a means 3a minus 1, so 2 here, minus 6 here, and 9 here, 3 here, and minus 6 minus 1, so minus 7 here is equal to 0. Okay, now if you open it, I think you get 3 beta is equal to 1. If you simplify it, you will be getting the value of 3 beta to be equal to 1. So what they are asking is 9 beta, so answer would be 3. So answer would be 3. Isn't it simple question? See, you will not dare, I am saying dare, to find a power 7 in the exam. Are you getting it? Even if you think that a determinant of a is equal to minus 1, so let me take a power 5 out, that can also be possibility. So in that case you need to make a square minus beta minus 1 into a minus beta into I is equal to 0. If you throw a power 5 out, then this determinant has to be equal to 0. Now you have to find the a square. Okay, and then a multiplied with beta minus 1, I multiplied with beta, and then collecting all the terms, making this determinant equal to 0, you will definitely get 3 beta equal to 1, but it will take time. Okay, so that's why I'm saying whenever you see this kind of expression, the first thing that should come in our mind is Cayley-Hamilton theorem, characteristic equation. Okay, now I have done I think some 4 or 5 previous year questions. Now coming to eigenvalue, this is also important. I have seen few questions JEE Advanced, mains also I have seen it. So eigenvalues, what is eigenvalue? Please see, I told you that a minus lambda I is the characteristic equation. Okay, and it will be quadratic or cubic or biquadratic depending upon the order of a. Now the roots of this, let's say roots are alpha 1, alpha 2, depending upon what is the degree of this polynomial equation, you will be having that many roots. Now these roots are called eigenvalues. Alpha 1, alpha 2 and so on are called eigenvalues. So bachcho, we don't, I think so we are not doing anything new. We already know what is this characteristic equation. Just the roots of that characteristic equation are called eigenvalues. Let me give you brief theory about eigenvalue and eigenvector. Actually what happens, suppose A is n into n order matrix. Suppose A is n into n order matrix, okay, and there is one n into n, and there is some x, that is xij, and this is n into one order matrix. That means it's a column matrix. Sometimes we also call this as a vector. Now if you multiply a with x, we will be getting n into one order matrix only, a into x. Okay, we will be getting n into one order matrix only. Okay, now if we select a certain column matrix x, so that when this multiplied with x, a multiplied with x, give you scalar multiple lambda times x, scalar multiple of same column matrix x. Okay, I hope you are getting it. See, a when multiplied with n into one order matrix will be some, let's say b, and that will also be n into one order matrix. Now we want this and this lambda times x to be same for certain lambda. Lambda is a scalar quantity, x is the same column matrix. Okay, this will be valid for very few values of lambda and few selected column matrix x. So in this case, this x is called as eigenvector. This is called eigenvector, and lambda is called corresponding eigenvalue. Both have same short forms EV, so I have to write eigenvector and eigenvalue. Okay, so this is the theory. Now why this equation, characteristic equation, is involved here? Now if you rewrite this relation, here, let's say, so it will become A minus lambda I determinant, sorry, this will become, what is happening? Something is wrong. Yeah, this will be A minus lambda I multiplied with x is equal to 0, is equal to null matrix. Okay, here on this eigenvector, that is column matrix x, the condition is, maybe I have forgot to tell you, the condition is that x is a non-zero matrix. So if it is non-zero, then we have to have A minus lambda I to be singular, means its determinant has to be equal to 0. There is a property in matrix we do that whenever A into B product is null matrix and B is not null, if suppose two matrix, let's say P into Q, their product is null matrix, okay, and Q is not null, then P has to have its determinant equal to 0. So that's the same thing. Okay, so if x is not null, so this can happen only if this kind of equation is there. So if you solve it, you get characteristic equation. The root of this characteristic equation are called as the eigenvalues, as I told you. Okay, now what are the advantage of these eigenvalues? Let's see. But for that we need to understand few properties. Okay, and they are very simple properties. They are just like if you remember transformation in quadratic equation. First, suppose alpha 1, alpha 2 and so on, they are eigenvalues of a matrix A, Okay, then alpha power 1, alpha 1 power 2, alpha 2 power 2 and so on, they are eigenvalues of A square. So what happened? If you do the A square, your eigenvalues will become square of all corresponding eigenvalues. If you take power minus 1, alpha 1, alpha 2 and so on, minus 1 actually, not minus 2, minus 1 and so on, they will be eigenvalues of A inverse. Okay, similarly in general, if I say, if you want alpha 1 power n, alpha 2 power n and so on, they will be eigenvalues of A power n. Okay, so from A we get this A power n having these eigenvalues. In fact, if you multiply A by K, okay, your eigenvalues will be K into alpha 1, K into alpha 2 and so on are the eigenvalues of K into A. Okay, so these are few things that I am talking about here, and then I'll show you the use of this thing in our questions. Okay, the proof of these properties, like why alpha 1 square, alpha 2 square will be eigenvalue of A square and all, I have given in my session notes. Please go through it. Yeah, one thing before I start doing the question, before this question, one thing, suppose alpha, beta, gamma are eigenvalues of 3 into 3 order matrix, 3 into 3 matrix A. Okay, so as I told you, for A, the characteristic equation is this minus trace of A into lambda square plus trace of adjoint of A into lambda minus determinant of A equal to 0. And the roots of the same thing is alpha, beta, gamma. So sum of roots, sum of eigenvalues alpha plus beta plus gamma will be trace, and that is true for all. Actually, this is true for all order, true for all orders, like you can say n into 1 also. That means sum of eigenvalues will always be trace of that matrix. Then alpha beta plus beta gamma plus gamma alpha, that is equal to trace of adjoint of A. But this is not true for all. This is true for only 3 into 3. Okay. Now the last one, alpha beta gamma, that is the product of all the roots, will be equal to determinant of A. And that is also true for all matrix, all square matrix actually. Okay, so these two things are very important for us. Sum of roots will be trace, and product of roots would be the value of determinant of that matrix. Okay, these two things we have to learn by heart, and we will use these in questions and see how this makes our life simple. So this is one question of 2020. Here we are given trace of square matrix is defined to be the sum of diagonal entries. In fact, in your JEE advanced syllabus, even trace is not mentioned. So that's why they are defining it in the question itself. Okay, if A is 2 into 2 matrix such that trace of A is 3 and trace of A cube is minus 18, then the value of determinant they are asking. Now please see from this first line, can I say that if alpha beta are the eigenvalues of A, if alpha beta are the eigenvalues, then we are given alpha plus beta is equal to 3. Okay, if alpha beta are the eigenvalues of A, then eigenvalues of A cube would be alpha cube beta cube. Okay, and we are given alpha cube plus beta cube is equal to minus 18. Okay, now they are asking the value of determinant of A. That means they are asking you to find the product of eigenvalues, isn't it? Alpha into beta. So from these two relations, I think it is very easy to find. Just do the cube of this. So 3 cube, that is alpha plus beta whole cube, will be alpha cube plus beta cube. I think that's the formula. Plus 3 times alpha beta into alpha plus beta. I think you solve it. Alpha beta, I think comes out to be 5 if I'm not wrong. 3 into 3. 9 into 5, 45 minus 18, yeah, 27. So this comes out to be 5. So answer is this. Now people have done by taking certain values A, B, C, D. That way also it can be done. But I think this method gives you more confidence. Less time is needed to solve this kind of question. Now I have taken one question from my side that is not previous year. Now we are given A is equal to this and we have to find a trace of A power 10. Normally what we do, we try to find out some pattern in the value of trace of A square, A cube and so on. But if you know how eigenvalues work, I think it will be easy. Now A minus lambda I equal to 0, if I do, it will become lambda square minus, I think 3 lambda is the trace, and plus determinant value is I think 2. So the eigenvalues are 1 and 2 for A. So can I say directly for A power 10, the eigenvalue should be 1 power 10 and 2 power 10. Now if these are the eigenvalues of A power 10, so the trace of A power 10 will be just 1 plus 2 power 10. I think 1025 answer. Okay, now if you try to find the pattern for A square, A cube and so on, you can see and you will find it will be 1 power n plus 2 power n always. Here you can see it is 4 minus 1, 3. So it is coming out to be 3 for n is equal to 1. And then if you do A square, A cube, always for any n, 2, 3, 4, 5 up to 10 or more also, you will always get the trace equal to this thing. Okay. One more question I have taken here. Trace of P is equal to 0. We are given where P is a 3 into 3 matrix. We have to find trace of P cube minus determinant of P. Now I think very simple. If trace of P is 0, and if I assume eigenvalues of P to be alpha, beta, gamma, so sum of these roots is equal to 0. Okay, for P cube, the eigenvalues becomes alpha cube, beta cube, gamma cube. Okay, and sum of P cube is nothing but the sum of its eigenvalues. So that will be alpha cube plus beta cube plus gamma cube. Okay, because alpha plus beta gamma is 0, alpha plus beta plus gamma is 0. So from that identity, it has to be 3 times alpha beta gamma. I think we are done. This alpha cube plus beta cube plus gamma cube, alpha cube plus beta cube plus gamma cube will be here trace of p cube, and that is equal to 3 times determinant of p. Can I say that? Because product of eigenvalues is always determinant of that matrix. So the value here will be 3 only. So answer. Okay. I remember I did one thing when I solved this in your notes. I just told one thing, that AB minus BA. It is out of, not out of context, but it is different from this question. If you solve AB minus BA, I think you know the trace of AB, trace of BA are always same. Okay, so this will always have trace to be equal to 0. Trace of AB minus BA will always be 0. So you can see that whenever you are having A and B as 2, 3 into 3 matrix, this AB minus BA will satisfy this thing. That means trace of this cube minus determinant of this will always be equal to 3. In fact, this can be a property for any matrix that has trace equal to 0. I just mentioned that this thing also have trace equal to 0. So you can apply this thing here also. Now one more question, bacho. M is an orthogonal matrix whose determinant is equal to 1. Okay, we have to prove M minus I equal to 0. Okay. So please understand this thing. First of all, when we say orthogonal, orthogonal means M into M transpose is equal to I. Okay, so the M inverse is equal to M transpose. That is one thing. Now, they are asking the determinant of M minus I equal to 0. So maybe they are trying to say it to you that one of eigenvalue has to be equal to 1. Eigenvalue has to be equal to 1, isn't it? Then only you can say M minus I determinant is equal to 0. Okay, now let's see how we can say for orthogonal matrix whose determinant value is 1, its one of eigenvalue will be 1. Please see. See, if M is having eigenvalues to be alpha, beta, gamma, okay, we know M transpose, just changing row into column, column into row, you will get same characteristic equation. So its eigenvalue should also be alpha, beta, gamma. Okay, so for M transpose, they have to be same eigenvalues, but because M transpose is M inverse, so these eigenvalues has to be for M inverse also. For M, eigenvalues are alpha, beta, gamma. For M transpose, because they both have same characteristic equation, because M transpose is just transposing rows into column, column into row, so get same characteristic equation. So same eigenvalues for M, MT, and because MT is equal to M inverse, so this will also have same eigenvalues. But you know, if M is having eigenvalues alpha, beta, gamma, then M inverse should have eigenvalues to be 1 upon alpha, 1 upon beta, 1 upon gamma. Now, what does this mean? This means the set of eigenvalues alpha, beta, gamma of M and the set 1 upon alpha, 1 upon beta, 1 upon gamma, they have to be same. And also, determinant of M is 1, so alpha, beta, gamma also have to be equal to 1. Okay, now please see, if these two sets are same, okay, and let's say they are not 1, then suppose they are not 1, then or minus 1, then alpha will not be equal to 1 upon alpha, alpha will not be equal to 1 upon alpha, beta will not be equal to 1 upon beta, maybe alpha will be equal to 1 upon beta, then beta will become equal to 1 upon alpha, obviously. So this becomes this becomes this, then you are left with gamma and 1 upon gamma. Okay, now please see, if alpha beta is equal to 1, and because alpha beta gamma is also 1, so that means your gamma has to be equal to 1. Are you getting it? Suppose one of them is 1 or minus 1. I'll talk about minus 1 also. Suppose none of them is 1 or minus 1, then this eigenvalue alpha has to be equal to some other eigenvalue here, 1 upon beta. In that case, your third eigenvalue have to become 1. You cannot say that none of them is 1. Okay, now if alpha is minus 1, okay, then maybe they too will become -1 only. Okay, and then, and suppose beta is also -1, they will also be equal to -1. Then again gamma is nothing but 1 only. Okay, now if this is only -1 and none of them are 1 or -1, I think that is not possible. You can check. So what I'm saying, with that property of eigenvalue, if alpha, beta, gamma are eigenvalue of M, where M is orthogonal matrix, 1 upon alpha, 1 upon beta, 1 upon gamma are the eigenvalues of M inverse, and because they have same eigenvalues, they should be identical sets. So we have to have one of eigenvalue to be equal to 1, and hence done. Okay, that is one method. This you can do otherwise also. There is one more method, by writing I as M into M transpose and taking M common. That way also it can be done, but I'm talking about right now eigenvalue eigenvector thing, so that way I'm doing it here. Okay, now few important properties to know about eigenvalues. I talked about if A multiplied with K, A square, A inverse, A power n, how we get eigenvalues. Now few more important properties, please see. See, these things I have seen used in certain questions, not directly. I have not seen many questions in JEE Advanced, honestly speaking, but I think they will be good thing, they will be important thing for you to know, so that you can do some high level questions easily. Yeah. So the first thing which I am talking about, 3.2, 3.1 was that property that I talked there. Now 3.2, if K is eigenvalue of A into B, if K is eigenvalue of A into B, then my claim is K is eigenvalue of BA also. And I have given proof of this in my notes again, so you can go through there. K is eigenvalue of AB, then K is eigenvalue of BA also. Very important thing, very useful thing. Okay, now if that is so, please listen carefully. You should have, suppose A is 3 into 3, B is 3 into 3. Okay, the product AB will be 3 into 3. So then AB, that is 3 into 3 matrix, will have all the 3 eigenvalues same as all the 3 eigenvalues of BA. So they will have same characteristic equation. So this and this have same characteristic equation. Can I say that? Because if their eigenvalues are same, so they should have same characteristic equation, and this means their trace should be same, and I think that's a property. Because from that characteristic equation, if you remember, lambda cube minus trace of A into A lambda square, and then trace of adjoint of AB will be equal to trace of adjoint of BA. Okay, and then determinant of AB, I think we know it is equal to determinant of BA. Okay, so if K is eigenvalue of AB, then K is eigenvalue of BA. This lets you to prove it in just one line, isn't it? In fact, there is one interesting thing, let me tell you. Yeah, the one interesting thing here, I'll use this slide. Sorry. Suppose A is, let's say, M into N, and B is N into M. I have mentioned this thing in my notes also. Okay, then if you multiply AB, its order would be M into M, and if you multiply BA, its order would be N into N. Okay, and let's assume my M is bigger than N. Okay, now very interesting thing. As I told you, eigenvalue of AB should be eigenvalue of BA also, but you can see N is lesser than M. So this will have N eigenvalues. Okay, whereas it should have M eigenvalues. Okay, now interesting thing is that all N eigenvalues of BA also eigenvalues of AB But what about the remaining m minus n eigenvalues of AB? Okay, now please see, then remaining eigenvalues of AB, how many remaining values? I think it is m minus n. Okay, they have to be 0, 0, 0. They all have to be 0, 0, 0, 0, 0. Okay, now how this is important, please see. You might have seen such questions in some advanced papers, advanced books, where they ask you that A is 3 into 2 and B is, let's say, 2 into 3. When you multiply A with B, you get 3 into 3. When you multiply B with A, you get 2 into 2. Okay, now as I told you, its two eigenvalues would be, let's say, alpha beta. Then its two eigenvalues will be alpha beta and the remaining will be 0. Okay, now based on that, can I say the determinant of AB in such case will always be equal to 0? Because it is given by the product of eigenvalues. So here, whenever there is a difference between m and n, the bigger order multiplication AB will have determinant value always equal to 0. So that is something that we can derive directly from it. Okay. Yeah, one more thing I have to tell you that I will do. 1 minute. Can I? Yeah. Okay, so this slide I'll use here. You remember skew symmetric matrix. Okay, so the property 3.3, I will say, for any skew symmetric matrix, I have given proof of this also. For any skew symmetric matrix A, eigenvalues are purely imaginary only. And what is purely imaginary? Like iota times alpha, iota times beta, in fact with plus minus, if skew symmetric matrix with real entries, yeah, that is also important, with real entries. Eigenvalues are purely imaginary only, like plus minus alpha, iota alpha, plus minus iota beta. In fact, 0 is also purely imaginary. If you remember in complex number, 0 is purely imaginary, and so on. Okay, so how it is important, please see. Suppose your eigenvalue is of order n into n, where n is odd. Okay, now because all the entries of A are real, so from the theory of quadratic and polynomials, its imaginary roots will be in conjugate pair. Okay, so the eigenvalues, which is nothing but the roots of that characteristic equation. So eigenvalues would be like one root is iota alpha, then other would be minus iota alpha, and so on. But because order is odd, so there have to be one separate root, and that have to be 0. Are you getting it? Because these kind of roots will be always in pair, and because order is odd, so one root has to be 0. And because one root has to be 0, if you remember, the determinant of A will be equal to 0 for odd order skew symmetric matrix. In fact, for even order, it becomes perfect square. So here you can see it will be alpha square into beta square types the value of determinant if it is even order, and these are the eigenvalues. Okay. So this question, I think, very straightforward question. For any skew symmetric matrix A, prove that this not equal to 0, this not equal to 0. It is like trying to have eigenvalue equal to 1, isn't it? But for skew symmetric matrix, as I told you, eigenvalues are always purely imaginary. So lambda cannot be equal to 1. So neither this true, neither this true. In fact, for any skew symmetric matrix A minus lambda I, if you put any real value of lambda, you can never ever get this determinant equal to 0. Okay. Now this question, prove that A is 5 into 4, B is 4 into 5 matrix, then we have to find this. Now please see, 1 minute, I will do one question before that. Yeah, then I will come to this question. Yeah, this question. AB is a matrix of 3 into 2 and 2 into 3 respectively. Their product AB is 3 into 3 given by this, and BA is non-singular. We have to find the value of determinant of BA. Okay, now tell me, AB we are aware of. Now for this AB, I can write characteristic equation lambda cube minus sum of roots, that is some trace actually. So that will be 5 plus 5 plus 8, I think 18. Yeah, 18. Okay, then the cofactor elements of diagonal elements, you can find that. I am not writing it. So it will be trace of adjoint of AB. Okay, and you can check the determinant value will be 0 here. You can verify it. The value of determinant of this would be 0. Okay, now if I simplify this equation, take lambda out, we will be left with a quadratic that will be like this. Now do you understand that the determinant of BA has to be this thing only, because that is actually the characteristic equation for BA. Why I am saying so? Because as I told you, BA, if it is having two eigenvalues alpha beta, its eigenvalues would be alpha beta and 0. Now this 0 has been taken out. If 0 is taken out, the remaining thing has to be corresponding to B into A. So this constant value will be the value of determinant of BA. Now you just have to find three cofactors for this, and take the sum of this. You will get the determinant value of BA. That's it. Okay. Now coming to this question, prove that if A is 5 into 4 matrix, B is 4 into 5 matrix, then we have to prove this determinant with this determinant equal to 0. Now how this can be done, please see. I have throughout used this characteristic equation given by A minus lambda I. Okay. Now when you open it, if you open it directly, for 2 into 2, you will get lambda coming with lambda square, leading term coming with positive sign. Okay, this minus trace of A into lambda plus determinant of A is equal to 0. But if A is 3 into 3 order, and if you open it, you will see, while simplifying it, your leading term will come with minus sign, and later on we multiply it with minus sign, so we get lambda cube minus and so on. But if you open it directly, you will be getting minus lambda cube plus trace of A into lambda square minus and so on. Why I am talking about all this? Because if we are writing it like this, A minus lambda I, your leading term will be this, then second leading term and so on. So here leading term will be plus or minus depending upon your A is even order or odd order. But let me know, if I, instead of using this, I use lambda I minus A. Okay, if I use lambda I minus A as my characteristic equation, it is just plus or minus 1 multiplied with this thing, isn't it? If A is even order, then plus sign. If A is odd order, then minus sign. Why I'm talking about this here, I'll tell you, but I'm sure you will understand. In this case, your leading term will always be plus 1. Okay, so that is what I'm going to use here. Why I'm doing this, please see. Suppose for A, that is 5 into 4, and B is 4 into 5. So if I do AB, I think AB will be 5 into 5 order, and BA will be 4 into 4 order. Okay, now for AB, if I write the characteristic equation, and this time I am writing lambda I minus AB. Okay, it will be a 5-degree equation whose roots will be 5. Okay, similarly, if you write lambda I minus BA, it will be 4-degree. Its roots will be 4 only, and let's say its 4 roots are lambda 1, lambda 2, lambda 3, and lambda 4. Okay, so as I told you, all the 4 roots of BA will be 4 roots for this also. So that will be lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3, and lambda minus lambda 4. but there has to be one extra root, and as I told you it is 0, so that means the corresponding to that 0, this will be the factor, and leading term is always 1, so there is no need to write anything else. Now for this thing, these 4 terms, and for this, these 4 terms, they are identical. This means, can I say on the next slide, that when this determinant multiplied with lambda will become identical to this thing? What I am saying, when this determinant multiplied with lambda will become identical to this thing. So what I am saying here is, plus. So what I am saying here is lambda times lambda I minus BA, because it was a 4-degree polynomial, will be identical to lambda I minus AB, which is a 5-degree polynomial. Why? The 4 eigenvalues here are same as 4 eigenvalues here, but this is having one extra eigenvalue 0, so corresponding to that lambda is coming here. Now this is identity, should be true for every value of lambda, including -1, because I want -1 here. So if I put lambda is -1, it will be -1 into minus I minus BA is equal to minus I minus AB. Now because BA is 4 into 4 order, so -1 if you take outside, -1 power 4 will go out, so it will be just minus sign only. So I plus BA, wait, I think I need lambda to be 1. My mistake, lambda I have to use at 1. Actually we can take any value of lambda. This will be decided by what is asked to be proved. What is asked to be proved. So here they are asking us to prove I minus BA, so I will be putting lambda is equal to 1. So this, and here I minus AB. Now if I write this as, because they are asking us to prove AB minus I and BA minus I. So if I write this as BA minus I, because it's a 4 into 4 order, -1 power 4 will come out, so that means 1 only. Whereas here -1 power 5 will come out, -1 power 5. So this is actually AB minus I into -1. So if this taken that side, I think we get our answer. Okay, so I hope you have understood what I was trying to tell you. Now I have taken all these questions based on what I taught you in this class. What we have done: characteristic equation, Cayley-Hamilton theorem, then use of all these things, then eigenvalue, eigenvector, then properties, and the use of those properties. Okay, now proof of all these things that I have talked about, including Cayley-Hamilton theorem, eigenvalue, eigenvector, those properties, everything is there in the session notes. Please go through it. So that is all for this session. I'm sure you would have liked this session. Thank you so much. Bye everyone.